This video is about problem 7.24. It is about a mass that is compressing a spring by a distance delta x. The spring is let go for some distance d, and this distance is not enough to make it back to the equilibrium of the spring. And the problem asks, after traveling this distance d, what is the speed of the mass? Now we can solve this problem by doing sum of forces equals ma. We do a body diagram. We know that we have a normal force and a weight. We have a force on the spring that goes to the right and a force of friction that opposes the motion to the left. But this force in the spring is going to be proportional to x. Therefore, it's not going to be a constant acceleration, and I would have to do an integral. From the body diagram, I do get something useful, that the normal force will have the same magnitude as the weight. So what type of problem are we dealing with? I could do sum of forces equals ma, but I can also remember that I can solve these type of problems with conservation of energy. That the change in kinetic energy plus the change in potential energy must be equal to the work done by friction, which is always negative. Like every other conservation of energy problem, we'll do some accounting of the energy. It is initially at rest, so the kinetic energy initially is zero. It is always at the ground, so the gravitational potential energy will be zero both initially and finally. The elastic potential energy will be depending on the compression of the spring, which will be delta xi. At the end, it will have some kinetic energy with a speed df that we're trying to find. And it will still have some potential energy, since it is still compressed by a little bit by delta xf. Since there is friction acting on the system, there will be some loss of energy that will go to heat up the track. And the work done by friction will be the force, which is proportional to the coefficient of friction times the normal force, times the cosine of the angle between the force and the displacement, times the displacement. The normal force will be equal to mg from the body diagram that we found. The cosine of the angle will be -1, and from this we get that the work done by friction will be proportional to negative mu k mgd. Alright, so we got all the physics down. We go back to the original equation and we write down the final and initial kinetic energies to find the change in kinetic energy. We do the same to find the change in potential energy. There was no change in the gravitational potential energy, but some in the elastic potential energy. And then we set that equal to the work done by friction. We should always be negative, since it's not going to help you gain energy, it's going to make you lose energy. So then we can solve for the kinetic energy final by doing some rearrangement with algebra, so that we can find the final speed of the mass. So after this, it's all just rearrangement and plugging in whichever numerical values they gave you. But to quickly summarize how we did this, we recognized it was a conservation of energy problem, and that there was work done by friction, so some of that energy is going to go to heating up the ramp and will be lost from the total mechanical energy. So we found the initial kinetic energy, initial gravitational potential energy, and initial elastic potential energy, and wrote down expressions for all of those. Then we did the same, but for the final one. Then found the work done by friction, plugged everything in, and solved for whatever we needed. Alright everyone, I hope that was useful. Thank you.